Today I'd like to give you a short introduction to our upcoming course, just to give you the idea of the style and presentation so you can taste the flavor. The point is pure mathematics without applications feels sometimes a little dry, so whenever possible we will always discuss physics applications of each mathematical technique we explain. Therefore, for an introduction, let us discuss some celebrated experiment and its theoretical explanation. So we go back to 1988, open an ancient physref letters, and here is the paper we are looking for. Quantized conductance of point contacts in two-dimensional electron gas by Van Wees and the rest. The group from Holland was exploring experimentally the conductance of the quantum point contact and discovered that under certain conditions the conductance forms a quantum staircase as a function of the gate voltage. Before we go any further, let me give you a brief remark about what a quantum point contact is. The quantum point contact is formed by the two-dimensional electron gas and gate electrodes, which control its shape. The two-dimensional electron gas, in turn, is formed at the interface of the heterostructure, for example, at the interface of gallium arsenide and aluminum gallium arsenide. To explore the conductive properties of the two-dimensional electron gas, the experimentalists control its shape by gate electrodes. They put charges on them and create repulsive static electric fields in the plane of the interface. This way, one can create a constriction so narrow that one can squeeze only a few electron waves in between. Therefore, the electrons ought to reveal their quantum nature when they pass through the constriction. One can then, for example, apply transport voltage and study a charge transport and how it is influenced by the quantum nature of electrons. Let us elaborate a little bit more on how the shape of quantum point contact is formed. What is happening here is that the electron field forms the potential well, or rather a bathtub, with electron liquid poured inside. It is interesting to know that the potential well forms a quantum barrier for electrons in longitudinal x direction as well as the expected confining transverse barrier in y direction. So the critical region looks like a saddle. The level of electron liquid is defined by their energy, that is, their chemical potential. The H of the quantum point contact is formed by the classical equation of motion, namely by the condition when potential energy of the electrostatic gate field becomes equal to the electron's chemical potential. The experiment revealed the following beautiful phenomenon. As they were gradually widening the quantum point contact, the conductance of the contact was changing stepwise, forming the even staircase. The height of each step was equal to the universal quantity, the so-called conductance quantum, E squared over h, where E is the electron's charge and h is a Planck's constant. The interesting thing about this quantity is that it is composed only of fundamental physics constants. Actually, it's not so difficult to figure out why this is happening, at least qualitatively. Let us return to our potential well. Right, let us see how we can achieve the widening of the constriction. Basically, in the experiment, they simply change the gate voltage, or effectively, the chemical potential of the electron liquid. As you can see, as the level of the liquid rises, the classical H of the contact and constriction, in our case it's a simple horizontal cross-section, widens. Now, let us focus on the vicinity of the constriction. The electron's motion in transverse direction is confined, but wait, confining motion in any direction always entails the quantization of energy. So the energy associated with the transverse direction is quantized. And here is the explanation. To widen the contact, we raise the chemical potential of electron liquid. As the level of the liquid crosses yet another energy level, new electron propagation mode is unlocked. As a result, we have a leap in the conductance. Now we are ready to talk about the mathematical aspects of the quantitative theory of the phenomenon. First, let us discuss a little more the saddle shape of the potential barrier. The first question is why it is a saddle. Well, to understand it, let us approximate its transverse cross-section by a parabolic function. It is in an extremal point in y direction after all. So u is equal to alpha y squared over 2. If the potential is purely two-dimensional, it ought to satisfy a 2D Laplace equation. Hence, if the y dependence is y squared, then the x dependence must be negative x squared, so the Laplacian of the potential vanishes. This way, we come to the following form of the potential. And here is the classical saddle shape. Notice that x and y enter symmetrically. In reality, the potential is of course not two-dimensional. However, when we consider the more realistic 3D case, its saddle shape is retained. The only change is that it loses its symmetry with respect to x and y, so the model potential is as follows. So our plan is to solve quantum equations of motion for electrons and obtain the quantitative results for the conductance. Accordingly, we proceed to write down the Schrödinger equation with our model potential. Here it is. This is a 2D differential equations with partial derivatives. There is a standard mathematical procedure to reduce it to simply one-dimensional equations. It's called a separation of variables. So our plan is as follows. First, we separate the variables and show that the motion in longitudinal direction indeed can be easily detached from the simpler one in the transverse direction. Second, we explore the exact solution of the one-dimensional longitudinal motion. Now let us separate the variables. Fortunately, the potential itself is separable, meaning it can be split into a direct sum of x and y dependent terms. The first step is to split the wave function psi into the product of x and y dependent components. Accordingly, we split the total energy of the electron into transverse and longitudinal parts. The second step is to divide the equation by the wave function itself, psi. The third step is to put x and y dependent parts into different sides of the differential equation. At this stage, the separation of variables is already manifest. Indeed, since the left-hand side doesn't depend on y, changing y in the right-hand side doesn't affect the left part of the equation. Therefore, the left-hand side is constant. Hence, the right-hand side is also equal to the same constant. Without loss of generality, we may put this constant equal to 0. As a result, instead of a single two-dimensional differential equation in partial derivatives, we now have two one-dimensional homogeneous differential equations. We see that the equation in transverse direction is completely detached. The message of this equation is very clear. It is the simple one-dimensional harmonic oscillator Schrödinger. And we come to a simple equidistant energy quantization in the transverse direction. The second equation is an infinite motion in the field of inverse parabolic potential. It is the solution of this equation that defines the quantitative staircase structure of the conductance of a quantum point contact. Therefore, the equation is going to be the central topic of our introductory lecture. Here is the schematic energy diagram of the potential and the incoming electron. We see that the potential forms a scattering barrier for the electron. Quite naturally, the transmission of electron through the quantum point contact is reduced to the solution of the scattering problem in one-dimensional potential barrier. Physically, we expect that far from the maximum of the potential, where the scattering event intuitively occurs, the wave function is the combination of incoming and reflected parts to the left of the contact, and the transmitted outgoing wave to the right of the contact. Here I'd like to point out that the potential is a smooth and simple function of coordinates, and one would naturally expect that the solution far from the right of the potential will the simple smooth continuation of the solution to the left. So the incoming wave smoothly turns into the outgoing wave. But something strange and unique is hidden in the structure of the equation, some kind of obscure singularity or something like this, since along with the incoming wave, the additional reflected wave solution ought to arise. So our goal is to find out how this happens and how the reflection and transmission waves are formed. We expect that the inner structure of the equation is such that somehow it facilitates the appearance of this reflected wave. Let us make the equation dimensionless and introduce a suitable rescaling. First, rescale the coordinate, and then the energy. And we come to a slightly simplified equation. This equation has its own name in mathematical physics. It is called the parabolic cylinder differential equation. So what is so challenging about this equation? The answer is simple. Its coefficients. They are not constant. As you see, they are quadratic functions of x. Now let me state this clearly. There is no developed algorithm to solve linear differential equations with quadratic coefficients of a general form. So is it hopeless from the very beginning? Fortunately, it's not. Our equation is more symmetric, and we will find the way out. Let us investigate how this equation looks like far away from the scattering region x is equal to 0. Naively, we would expect that the solution looked something similar to a plane wave, which is a simple exponential. But here, the situation is slightly less trivial, since at large coordinates the potential energy, minus x squared, doesn't vanish. Its modulus grows and is much larger than the total energy of the particle, which is of the order of nu. Generally speaking, the behavior of the solution at large coordinates is called an asymptotic in math. As we will see in a minute, the knowledge of asymptotic behavior often helps to simplify most differential equations we encounter, let it be quantum mechanics or mathematical physics as a whole. So we need to find the approximate solution of our differential equation for large x. The first step is to drop 2 nu comparing to x squared in the second term. And this is our exact condition on x being actually large. Now we have a simplified equation. It looks very similar to a plane wave equation, with the only difference that the wave vector now depends on x. As you remember, the solution of the plane wave equation is a simple exponential. In the same spirit, we seek for the solution of our equation in a similar form. We make a change, psi is equal to e to s, where s is a new function. This kind of change is used so often in quantum mechanics, it has a special name for it. It is called a semi-classical substitute. Now, the first and second derivatives are straightforward. We plug the second one into our simplified equation and end up with the equation on S. Well, this doesn't look like a particularly bright idea after all. We started from a linear equation and ended up with a nonlinear one. It seems that even this simplified equation cannot be solved exactly. But we don't need the exact solution. We only want the approximate one, valid for large x. So we follow the standard path. Step 1. Make a simplifying assumption. Step 2. Build the solution based on this assumption. Step 3. Check if this assumption is preserved by the found solution. So here is our simplifying assumption. Suppose that the first derivative is much greater than the second one at large x. This assumption allows us to drop the term with the second derivative, and the equation immediately becomes trivial. We solve it for s. At this stage, we can already check if our simplifying assumption is satisfied. The second derivative is simply plus minus I. And indeed, s prime modulus is much greater than s prime prime modulus. So we are on the right track. Next, we perform a simple integration and finally obtain our asymptotic solution. Here it is. We get 2 signs. It is to be expected, of course. We solve a second order differential equation after all, so we ought to arrive at 2 linear independent asymptotics. Naturally, 2 signs in the exponent correspond to the left moving and right moving particle at large x. To see it, we may compute the particle flux. Actually, the average momentum will suffice. As we remember, the momentum operator in quantum mechanics is a simple derivative. The momentum average is the corresponding scalar product. And the following bilinear combination of psi's plays the role of momentum density. Let us plug in our asymptotics wave function psi and obtain the momentum density. Hence, the positive exponential describes a right moving particle for positive x and a left-moving particle for negative x. The same, with opposite signs of course, holds for the negative exponential. So the asymptotic helps us understand how the incoming and outgoing electron waves looks like. Armed with asymptotic solutions, we are ready for a final assault of our differential equation. First, let us remind ourselves that our solution should describe a scattering event. That implies that the solution at large positive x should look like the outgoing electron wave, so it's e to I x squared over 2. While at large negative x, it should take a form of the sum of incoming and the reflected electrons. Here, watch carefully for signs in the exponents. Therefore, we expect our solution to have the following asymptotic behavior. Now, there is one powerful way to simplify a linear differential equation which almost always works. If you are lucky enough to get the asymptotic, always try the following ansatz. Represent your initial function as a product of your asymptotics and a new function. So psi of x is equal to asymptotic times some new function phi of x. And rewrite the initial differential equation in terms of a new function phi of x. We face a choice which of the asymptotics to take, positive or negative exponential. At times, this choice may be quite fateful. Since we are interested in the solution that turns into a positive exponential at x tending to plus infinity, let us choose the asymptotic with plus sign. Besides, the plus choice leads to less trivial situation, and I'd like to share it with you today. We seek for the solution in the following form. Compute the first and then the second derivative and plug them in. As a result, we come to a new differential equation on phi of x function. Actually, we achieved a series simplification of our initial equation. The key point is that the quadratic in x coefficients have cancelled out, and we are left with the differential equation with the coefficients which have linear in x term only. The good news is there is a general algorithm to solve differential equations with linear coefficients. It is called a Laplace method. The central idea, as you may have already guessed, is to seek for the solution in the form of Laplace transform. An important point is that the integration range here can't be restricted to the real axis only. From the very beginning, we'll understand this integral as a contour integral in a complex plane. Hence the notation C for contour. To plug it into our equation, we need to perform differentiation with respect to x. Now x plays the role of the parameter of the integral. The differentiation is simple since we needed to differentiate the exponential term only. The first and second derivatives are as follows. And we plug them into our equation. Now we unite them under a sign of a single integral and regroup a little. And here comes the amazing trick which always works as long as the coefficient of your equation are linear functions of x. We rewrite the term with x as a derivative with respect to t, like that. Hence we introduce the derivative term under the sign of the integral. Next, we want to turn the integrand into the full derivative. Using the standard product rule, we identify g as an exponential function e to xt. The function f remains to be defined in a minute. Let us assume for a second that it exists. Then we can interpret our integrand as follows. As a result, the right-hand side of our differential equation is turned into a simple definite integral, which is trivially taken. As long as fg product takes identical values at the endpoints of contour C, the integral vanishes and the equation is satisfied for any x. We just need to check if the key function f exists. From the structure of the integrand, we extract two entangled equations on f and z. Dividing these equations, we get a simple differential equation on f. Elementary integration gives the expression for f and z. Notice that both f and z are multi-valued functions of t. The branch point is the origin of a complex plane T. To define them uniquely, we will need to draw a branch cut and fixate the suitable regular branch. As we will see soon, the position of the branch cut greatly affects the structure of the solution. Finally, we have the full ingredients to write down the exact solution phi of x, albeit in the integral form. Here it is. Phi is defined by the Laplace integral, while the wave function is related to phi function by a simple multiplication. Denoting FG product as a new function v, we set the condition for our contour. It should be drawn in such a way that function v assumes identical values at endpoints. Here, let us point out that v function is also multivalued with the same branch point. It also requires the branch cut for its correct definition. The Laplace type integral defining the exact solution can't be taken exactly. But we never need the exact solution. We need to solve the scattering problem. That is, we want to find reflection and transmission coefficients in the asymptotic form of our exact solution. These are the coefficients which eventually define the shape and structure of the conductance of the quantum point contact. So we are hunting for asymptotics. Now we come to the most interesting and non-trivial part of our story, the choice of the contour. Usually, it's way easy to integrate along the infinite contour of integration. So one generally prefers to stretch the contour in such a way that both ends lie at infinities in the complex plane. Keep in mind that v function assumes identical values at these distant points. This requirement usually outlines the proximate position of the contour. In fact, in most cases, it's easy to find the points at which v function simply vanishes. So let's explore the most significant terms entering v function. Obviously, it is an exponential factor. Therefore, the behavior of its exponent at infinity is crucial. We see that at large t, the exponent is dominated by the quadratic term. So, if we import the condition that the real part of the quadratic term tends to minus infinity at both ends of the contour, we will satisfy our principal condition. The v function will indeed vanish. Let us see how it comes about. We switch to exponential form of t, introducing its modulus and argument. And here is how our quadratic term is transformed. Extracting its real part and taking modulus rho to infinity, we deduce that it is enough to require the argument of t to satisfy the following equation, which is easily solved. The solution covers entire regions of the complex plane of T. These regions outline the position of allowed areas where the contour of integration can start and end. In our particular case, the regions in question are the second and the fourth quadrant of the complex plane. Keep in mind that these are the asymptotic regions. They are found for large T only, where the term xt can be dropped in the exponent of v function. Now we may draw at least the proximate position of contour C. There are three different situations. First, contour starts and ends at complex infinity in region 2. Second, contour starts and ends at complex infinity in region 4. And third, contour starts at infinity in region 2 and crosses to the infinity at region 4. Or vice versa, both contours give the same solution up to minus sign. Let us discuss the first two possibilities, namely when contour starts and ends at infinity in the same region. We know from complex analysis that one can smoothly deform the contour of integration without changing the value of an integral. The only restriction on deformation is that the contour can't cross singularities, like poles or branch points. The problem with the contour that starts and ends in the same region of a complex infinity is that it can be pulled to infinity entirely. On the other hand, we remember that the exponential function, which enters v function, as well as, pay attention, the integrand, which defines our solution, vanishes at these regions. Therefore, first and second contour positions are to be discarded. Position 3 looks more promising. One cannot pull the contour entirely to infinity without dragging it through the forbidden areas. To find the asymptotics of the solution at x tending to plus infinity, we use the standard technique which is created for Laplace type integrals with a large parameter in the exponential. Actually, a large chunk of the material of our course is devoted to this subject. Here I'll just sketch it. The large positive parameter in our case is of course the coordinate x. The Laplace type integral is the integral of the following form. To estimate it at large x, we use the following philosophy. The obvious thing is that the integral is dominated by the maximum value of the exponential function, that is, the maximum value of the real part of f of t. Let's denote the corresponding point t0. If x is large enough, the exponential function decays very fast. Therefore, the integral is dominated by a small vicinity of t0. As I'll explain in a second, this argument opens the road for a drastic simplification. There are two possible problems, though. The first one is that the point t0 most likely doesn't lie on the contour. The second one is even more serious. We integrate in the complex plane. The real part of the exponent, being the real part of an analytical function of complex variable, has no maxima or minima. It has only saddles. This is the fundamental property of analytical complex functions. So how do we tackle these two issues? First, let us have a quick look at the typical relief of the real part of exponent function. It looks like a mountain ridge, although with no peaks. The start point and end point of the contour are usually separated by some path across the saddle of the ridge. We therefore understand that though the real part of f of t doesn't have extrema in a complex plane, it's not a problem. It can still have maxima along the path. The larger the parameter x, the sharper the peak of the modulus of the exponential function. Second, we can always deform the contour so it passes through the saddle. Just notice that the peak becomes even sharper when we choose the right angle of the plane of the contour. So we see three things. First, the saddle is important. Due to the large x parameter, the modulus of exponential forms extremely sharp peak on some paths. It is the vicinity of a saddle that the main contribution to the integral may come from. To find this contribution, it is enough to approximate function f of t by its Taylor series near the saddle. And this is a drastic simplification I was talking about. Function f of t can be quite arbitrary and very complicated, but we just need a very small piece of information about it, namely its behavior in the tiny vicinity near the saddle point. Second, we need to deform the contour so it crosses the saddle at the correct angle in the sharpest possible way. This angle defines a very special direction on the relief of the real part of the exponent. It is the path of the steepest descent. By going along the steepest descent direction, we maximally shrink the important region for the integral. And our Taylor series expansion of the exponent of the exponential function gives ever better accuracy. Third, the behavior of arbitrary function g of t is not important as long as it's smooth in the vicinity of the saddle t0. Usually, it is indeed the case, so one can consider it constant near the sharp saddle and substitute with g of t0 while integrating. Let us use this philosophy to compute our integral. As we see, the integral defining our solution looks like the one of Laplace form, where the function g of t is simply t to minus I nu minus 1/2. The saddle of our exponential function f of t is given by its critical point equation. And here is the critical point. The value of the function f at the saddle is as follows. F is quadratic in t, so its second order Taylor series is in fact exact. For convenience, we introduce the parameterization of complex variable in the vicinity of the saddle. What is good about this parameterization is that the modulus of the complex number, rho, basically measures our deviation from the saddle, and the angle alpha is to be chosen in the steepest descent direction. So now we rewrite the function f of t as follows. As expected, the behavior of the exponent is quadratic in deviation rho. There are no linear terms. The real part of f of t looks rather simple. The steepest descent corresponds to the maximally negative deviation from the saddle. So we choose alpha such that sine of 2 alpha is equal to -1, and the trigonometric equation is trivially solved. Here integer n reflects the fact that the saddle can be passed in two possible directions. In our case, direction 3 pi by 4 is obviously the right one, as it corresponds to the general direction of motion along the contour. And we turn it into a straight line. The local parameterization, therefore, becomes the global one for the entire contour. And it makes the integral elementary Gaussian. The exponent is turned into a simple expression, and the integral is trivially taken, yielding the asymptotics. We see that it still contains yet undefined expression, minus 2ix to minus I nu minus 1/2, because we didn't specify the position of the branch cut of the multivalued function g of t. But let us forget about it for a second. At this point, the only information we need is the principal exponential behavior, which is e to minus ix squared. Then, the full asymptotics of the wave function reads as follows. But this is the left-moving particle instead of the right-moving one. And this is the ominous sign for us. Our last and most promising contour failed our expectations. The question is, have we counted all the possibilities? Well, basically yes. And we failed to get the solution we need. But we completely overlooked the possible influence of the branch cut. And now the final actor comes on stage. Not only the branch cut fixates the value of our multivalued integrand, it actually defines the behavior of the solution. Now our only chance is to start and end the contour in the same quadrant, but make it circle around the branch point. Therefore, the branch cut should also be placed in the allowed regions of the complex plane. The fourth quadrant is now good. The contour can be easily deformed to pass through the saddle point, leading to the wrong asymptotics. Our only chance is the second quadrant. This is the approximate position of the contour and the branch cut. Hopefully now we'll get the correct asymptotics at x tending to plus infinity. But how do we find the asymptotics right now? The saddle point won't contribute anymore. Well, we could technically stretch the contour and draw it through the saddle. But we will have to return to region 2, and we can always deform the contour in such a way that it cancels the saddle contribution on its way back. The saddle point, though, is not the only unique point of the integrand, and here Watson's lemma for loop integrals comes in very handy. We'll discuss it in great detail in due time, but now I'll again state it in the form that feels plausible. We see that at large x, apart from the saddle point, the integral has another important point that may potentially give rise to a significant contribution, and that is a branch point. Indeed, the real part of the exponential function assumes its maximum value at ever-growing t. So it seems reasonable to stretch the contour along the positive axis of t as far as possible to utilize the growth of the exponential function. The point is, we still need to return, and when returning, we can pass along the same route, cancelling the previous enormous contribution from the exponential. There is a subtlety here, though. This cancellation is happening until we reach the branch point. Starting from it and moving to the left, the lower and upper branches of the contour give rise to different contributions and won't cancel each other. Of course, to build a better estimate of the integral, we need to deform a contour along the steepest descent path, because we'd like only a narrow region to contribute. The crucial region for us is the vicinity of the origin, where the exponential function is maximal. Now, if we look at the exponent xt minus it squared over 4, we notice two things. First, near the origin at small t, the second term can be discarded. Even when the first term xt becomes of the order of unity, so t of the order of 1 over x, the second term is 1 over x squared, The integral therefore is greatly simplified. The exponent is turned into a simple linear function of x. Second, the steepest descent direction is simply the negative real axis. Indeed, it's more or less obvious that the exponential e to xt decays in the fastest possible way when t moves to the left along the real axis. At least, this is true for real positive x. Therefore, the branch cut shouldn't be an obstacle for the steepest descent path. We understand now that if we want the branch cut to facilitate the computation of the asymptotics, we need to draw it along the negative real axis. This reasoning finally seals the position of the branch cut. We draw it along the horizontal negative real axis. And here is the final picture of the position of the contour, the branch cut and the allowed regions in the complex plane. The branch cut fixates the regular branch of the multi-valued function g of t. We will assume that its argument is equal to pi on the upper bank and minus pi on the lower bank of the branch cut. The idea of Watson's lemma is therefore to drop all nonlinear terms in the exponential as insignificant and to deform the contour into the loop directed to the steepest descent of the exponential function. This way, we come to the following simplified integral describing the solution at x tending to plus infinity. Here it is. By making a simple change xt is equal to s, we reduce it to a known Hankel representation of gamma function. And here is our final answer for the asymptotics. And the full wave function now reads. This is what we need. This is the right moving particle at x tending to plus infinity. Now we come to the most interesting part. What happens to these asymptotics when we go from the right infinity to the left infinity? We know that the reflected wave should somehow appear. The best way to see how this is happening is to traverse from the positive x to negative x in the complex plane, retaining the large modulus of x. So let us rotate, say, it in the upper half plane. The first thing we notice is that the position of the saddle point changes, but the steepest descent path at the saddle stays the same as it doesn't depend on x. The situation at the branch point is the opposite one. The position of the branch point is obviously not changed, but the direction of the steepest descent rotates with rotating x. Indeed, let us remind that the steepest descent direction alpha is defined by the condition that when moving along the integration contour, the argument of the exponential function e to xt decays in the fastest possible way. When x was positive, that simply meant that the argument of t was pi, which was the negative direction of a real axis. But now x itself acquired a non-zero argument theta, so the condition is a little bit different. We see that while x is rotating counterclockwise, the steepest descent direction at the branch point rotates clockwise. But now we seem to have a problem. The upper part of the contour can rotate clockwise and follow the steepest descent direction. The lower part of our contour obviously can't. It is blocked by the branch cut. And here comes the interesting point. Let us recall that the branch cut is the means to put the multi-valued function on a single plane. What we can do instead is to slip below the branch cut on the other Riemann sheet of the multi-valued function g of t. This Riemann sheet is defined by the new range of the argument of t. The initial Riemann sheet, which we call the upper one, was swept by the argument in the domain from minus pi to pi. The lower one is covered by the range from minus 3 pi to minus pi. Now we can deform the contour in such a way that the contribution from the branch point is taken into account correctly by both branches of the contour. Here, for the sake of clarity, I made the upper Riemann sheet slightly transparent, so you can see better what is happening. But we need to be very careful at the allowed region, region 2, in which the contour should start and end, is not changed. So the contour can't travel all 180 degrees along the steepest descent direction. To keep its origin and end in region 2, it has to bend. One more amazing thing is that the saddle point enters region 2 and becomes within the reach of the contour. So not only it should bend, but by bending it, it can pass through the saddle point in the direction of the steepest descent. As you clearly see, the contour passes the saddle point twice in opposite directions, but now they won't cancel each other, because the forward and backward parts lie on different Riemann sheets and have different values. It is the additional contribution we were talking about before. Now, the asymptotics of a wave function at minus infinity will have two terms corresponding to the incoming and reflective electrons. This is how the physics behind the differential equation manifests itself. It is hidden in the structure of the branch points and Riemann surfaces. To get the reflected wave, we had to explore how the geometry of contour affects the extraction of correct asymptotics. We have already computed the contribution from the saddle point before, when it was on the lower part of the imaginary axis of t. Now, not much really has changed. We just need to take into account the correct argument of the function g of t. Otherwise, the answer stays the same. So here it is. For the upper branch of the contour lying on the upper Riemann sheet, the argument of t0 is pi by 2. The lower part of the contour belongs to the lower Riemann sheet, and the corresponding argument is minus 3 pi by 2. The difference is 2 pi as expected. And here is the contribution from the saddle point. The contribution from the branch point essentially doesn't change its analytical form. We just need to keep in mind that the argument of t, which enters the asymptotics via power function g of t, has rotated by minus pi. Therefore, the whole contribution from the branch point is simply multiplied by the following factor. That's it. So now our asymptotics is the algebraic sum of two terms. The first comes from the saddle point, while the second one is from the good old branch point. And finally, we get our wave function at plus and minus infinity. Now please watch carefully. It is the first term that describes the incoming wave. The negative exponential gives the momentum proportional to minus x, which at negative x gives positive momentum and right moving particle. We may normalize our solution so as to at minus infinity, the incoming wave has a unit amplitude. Just divide it by the cumbersome sum of exponentials and you will get the familiar scattering wave function. Now actually we need the modulus of transmission amplitude, t, or rather its square, which is the transmission coefficient. It's a simple algebraic exercise, and I'm not going to reproduce it here. Just use the mirror relation for gamma functions, and you should get for the transmission the following answer. This is a well-known result for the transmission coefficient in the inverse parabolic potential. Sometimes it's called a Fermi formula for the transmission, since it resembles the Fermi distribution analytical result. You may probably even recall that the Fermi function is basically a smooth step function, interpolating between 0 and 1. Finally, we are ready to get the exact shape of the staircase dependence of the conductance. We use the celebrated Landauer formula for quantum conductance. Here it is, where n is the number of transverse energy levels below the chemical potential of the electron liquid. Let us recall that the new coefficient is the energy of the longitudinal motion up to a scaling factor. The energy in transverse motion is quantized, so the new factor is simply the difference of the total energy, which is the chemical potential of electron liquid, and the energy in the transverse direction. Finally, we plot the conductance as a function of the chemical potential, or gate voltage. And here it is. As we see, it reproduces the quantum staircase obtained in the experiment with the correct height of steps. So it is the example of how complex analysis works to explain mesoscopic experiments in physics. And it's just the beginning. We will explain a lot of amazing applications in much more detail and slower pace in our course. So I hope you enjoy it, folks. Join in and you'll see a lot of more beautiful things.